Hello and very welcome. This is lecture 4 in the module Postgraduate Dynamics with the acronym msd780. And we will look at the forward dynamics of the pendulum rod that we have been discussing in the last few lectures. And just to introduce myself, my name is Dr. Lucas du Plessis and I am a senior lecturer in the Department of Mechanical and Aeronautical Engineering at the University of Pretoria. So expanding the mind map we've been using to discuss the pendulum rod in the last few lectures, we are expanding this mind map once again. Today we will look at the forward dynamic analysis of the pendulum rod, which is section 6 in this mind map. Okay, and what we are busy with, as you already know, so we're using the undriven and driven pendulum rod to explain the underlying principles behind Prof. Nick Ravesh's body coordinate planar multi-body dynamics algorithm. Right, so let's dive right in. The forward dynamic analysis of the pendulum rod, and there we will first look at for forward dynamic analysis, what does the unconstrained formulation look like? And then for the pendulum rod, which is obviously a constrained mechanism, it does have a kinematic joint. So that's why it's defined as a constrained mechanism. We will then focus in subsection 13.2 on the constrained formulation. Okay, so for the unconstrained formulation, and we'll look at examples of unconstrained mechanisms in a little bit. Just bear with me for a moment. So, unconstrained equations of motion can be expressed in the following general form. Okay, simply mass times, or the mass, or this is the mass or inertia matrix multiplied by the centroidal accelerations, or the accelerations of each body in the mechanism, the acceleration of the center of gravity of each body in the mechanism, and that equals the external forces that act on the center of gravity of each mechanism. Okay, so this is then, once again, just to recap, the unconstrained equations of motion, which can be expressed in general form as shown here in equation 13.1. Now, this equation may represent the equations of motion for a system of unconstrained particles, a set of unconstrained bodies, or an open chain system formulated by the joint coordinates. Okay, now we are obviously none of these are applicable to the pendulum rod that we've been discussing, and it's mentioned here for completeness sake. All right, so what can be of interest to us though is the unconstrained bodies. It can be of interest depending on what mechanism you want to analyze. But certainly the open chain system formulated by joint coordinates is not relevant in this module, but it is dealt with in Prof. Nick Ravesh's planar multibody dynamics textbook. Now, these equations 13.1 are treated as linear algebraic equations when the unknowns are the accelerations. Okay? When the unknowns are the coordinates and velocities, the same equations are treated as second order ordinary differential equations. Okay, and we'll speak about ordinary differential equations a bit more later on in this lecture. So, when treating the equations of motion as a second order or as second order differential equations, to integrate them numerically, two arrays are defined as. Okay, we've got array U consisting of the positions and the velocities, and array u dot consisting of the velocities and the accelerations of, let me just define that a bit better. So positions of the centers of gravity of each body in the mechanism, velocities of the center of gravity of each body in the mechanism, and accelerations of the centers of body, center of motion, center of gravity, sorry, of each body in the mechanism. Now, if we integrate the array u dot containing the velocities and accelerations, we obtain the array u containing the coordinates and velocities at each or at the next time step. Okay, so we integrate the array u dot containing the velocities and accelerations at the current time step, so that we can obtain the array u containing the coordinates and velocities at the next time step. Obviously, this requires a set of initial values for the coordinates and velocities to start the integration process. And just as an example, just to emphasize or to illustrate rather the difference between the vector u and the vector u dot, just as an example to illustrate what we mean by that. Let's consider this. So example 13.1 refers to example 7.1, and that is put in the text here at the bottom. Refer to the system of two unconstrained bodies in example 7.1. What we want to do is define the necessary integration arrays to solve the equations of motion for this system using body coordinate formulation. Alright, so just now let's just look at what the details of example 7.1 are. A system of two unconstrained bodies is presented in figure 711a. A spring connects the bodies at A and C, and a damper connects point B of body 1 to ground at Q. The gravity acts on the system in the negative y direction. The lengths of links 1 and 2 are 0,3 and 0,24 respectively, and the other constants are given in this block over here. Okay, so a lot of detail, but we are merely interested in defining the necessary integration arrays to solve the equations of motion using body coordinate formulation. Right, so let's look at what does that solution look like. Very simple. Okay, for the two bodies, the coordinates are defined as r1, phi1, r2, and phi2. Therefore, the integration arrays are constructed as u consisting of r1, phi1, r2, phi2, r dot 1 or r1 dot, phi1 dot, r2 dot, and phi2 dot. And similarly, the integration array u dot consists of the compounded column vector or column array of which consists of the velocities and accelerations of these two bodies. Okay, so it's very simple, a very simple example, and it's merely an example to illustrate that these integration arrays are indeed trivial to define for a mechanism. Okay, so alright, so we're still busy discussing the unconstrained formulation. So let's now look at initial value problems. We did discuss that, saying that we did mention the initial values. saying in this point over here, if we integrate the array u dot containing the velocities and accelerations, we obtain the array u containing the coordinates and velocities at the next time step. This is the point I was looking for. Obviously, this requires a set of initial values for the coordinates and velocities to start the integration process. Alright, so let's look at initial value problems, which is obviously what we are dealing with in this section. So most general purpose numeric integration algorithms are developed to solve first order differential equations. A first order differential equation is written as, and there you can see it, expression 13.3, u dot is a function of u and time. Okay. Now where t is referred to as the independent variable, t represents time, and u as a function of time is considered a dependent variable. Equation 13.3 has a family of solutions, u as a function of t. The choice of the initial value, superscript 0, u, serves to determine one of the solutions of the family. The initial value, superscript 0, u, could be defined for any value of superscript 0 t or time 0, although it is often assumed that a transformation has been made so that time 0 is indeed 0. This does not affect the solution or methods used to approximate the solution. So what Prof. Nikravesh is saying here is you can run your simulation for any initial time or superscript 0 t, any initial time and any end time. It does not affect the solution method presented here. So in general, if n dependent variables are involved and n first order differential equations are available, equation 13.3 is written in vector form as shown here in equation 13.4. With a set of initial conditions, okay, superscript u, boldface, superscript 0, boldface u. Now, in dynamics problems, t represents time and it may not appear explicitly in the equations. Okay, this is a repeat of what I just said. Alright, so now solving initial value problems involves a step-by-step process in which a sequence of discrete points, superscript 0t, superscript 1t, superscript 2t is generated. We can also say t0, t1, t2, etc. Okay, the point is we have a sequence of discrete points where we solve the initial value problems. Now the discrete points may have either constant or variable spacing. Delta ti equals time at I plus 1 minus time at instant I, where delta ti is the step size for any discrete point ti. Alright. Now at each point ti, the solution u as a function of ti is approximated by a number ui. Since no numeric algorithm is capable of finding u as a function of ti exactly, the quantity epsilon I, which is now the magnitude of the difference between the approximated u as a function of ti, and the actual ui is defined to represent the total error at t equals ti. The total error consists of two components, a truncation error and a round-off error. Okay, so the truncation error depends on the nature of the numerical algorithm used in computing UI. Alright, now in the planar multibody dynamics textbook, when the term numerical error is used, it is referring to the truncation error. And just once again, the truncation error depends on the nature of the numerical algorithm used in computing UI. So what is the round-off error then? The round-off error is due to the finite word length in a computer. Okay, so an algorithm can be categorized as either explicit or implicit. An explicit algorithm evaluates u at time instant I plus 1 as a function of the current time instant ti and the current value of ui. In other words, u as a function of the current time instant in one step. An implicit algorithm is an iterative algorithm. In these implicit algorithms, an estimate for the next u at instant I plus 1 is required to start the iteration of the formula. Now, in order to obtain a relatively good estimate for u at the next time instant I plus 1, an explicit formula can be used. This step is known as the predictor step. Then the implicit formula is used to correct the predicted value of u I plus 1. Now, this step is known as the corrector step. Normally, an algorithm iterates on the corrector step. Okay. Although there exist many algorithms for solving initial value problems, most of them are based either on Taylor series expansion or polynomial approximation. Algorithms that are based on Taylor series expansion require the derivatives of functions with respect to t. A k-order algorithm needs the derivatives up to k minus 1, and these derivatives in general are not readily available. Therefore, the higher order algorithms with better accuracy are not computationally efficient. So, let's look at what are the potential for polynomial approximation. A classical theory asserts that any continuous function can be approximated arbitrarily within any closed interval by a polynomial of sufficient high degree, even if the solution is not a polynomial. In view of this theory, a polynomial of sufficient high order can in principle be used to calculate u at the next time instant to any desired accuracy. A kth degree polynomial is referred to as an algorithm of order k. In practice, the amount of computation increases with the order of polynomial. In most polynomial approximation algorithms, information from previous time steps is utilized to compute u at the next time instant I plus 1. An algorithm that utilizes information from time steps prior to the current time step is called a multi-step algorithm. Now, the accuracy of an algorithm is directly proportional to its order. In general, the higher the order, the more accurate the algorithm can predict a solution. Now, another commonly used family of explicit algorithms is the Runge-Kutta, that can be considered as a revised form of Taylor algorithms. In planar multibody dynamics section 13.1.2, Prof. Nikravesh reviews the fourth order Runge-Kutta algorithm for those of you who are interested in looking at that. Okay, so that is a summary of the theory of initial value problems. Now let's look at integration time step. Now, an important issue in using a constant step numerical integration algorithm such as the fourth order Runge-Kutta is the selection of a proper step size. A large step size may cause erroneous results. A step size too small may yield accurate results while increasing the computation time too much. Therefore, it is important to choose a reasonably small step size to obtain accurate results without unnecessarily increasing the computation time. The size of the integration time step should be adjusted based on the natural frequencies of a system. The higher the frequency, the smaller the step size. Now, to demonstrate this concept, we consider the one-dimensional oscillating mass spring system shown in figure 13.1a. The equation of motion of this system is written as mass times acceleration in the x direction plus the spring constant times the deflection in the x direction equals 0. We can divide with mass and that gives us equation 13.8. Now this system exhibits an oscillatory motion, and therefore the solution to this differential equation can be assumed to be of the form x equals a times cosine of, in brackets, omega t plus phi, where a and phi are the amplitude and phase shift, respectively, that can be determined based on the initial conditions of x and x dot, x being the displacement, x dot being the velocity. Now, in this equation, 13.9, omega is the natural frequency and is equal to the square root of the spring stiffness divided by the mass. The period of oscillation associated with omega, the natural frequency, is 2 pi divided by omega, and we use the Greek letter tau to indicate the period. Now, if 13.8 is solved numerically, okay, let me just zoom out a little bit. If 13.8 is solved numerically, the step size delta t must be much smaller than the period tau. A reasonable value for delta t could be delta t smaller than tau divided by 10. Now, assuming that m, for our example, the mass is 1 kilogram, spring stiffness is 100 Newton per meter, the time period is found to be tau equal to 0.628 seconds, hence the integration time step should be less than 0.06, which is 1/10. slightly less than 1/10 of the period. Okay, as another example, consider the single pendulum shown in figure 13.1b. For a rod of length L and a mass m, the moment of inertia is 1/12 mL squared. Okay, and that is the moment of inertia about the center of gravity. Okay, if the only external force is gravity, the equation of motion in joint coordinate formulation is 1/3 mL squared theta double dot plus a half m mass times gravitational acceleration times length of the pendulum times sine theta equals 0. Okay, and you will recognize this equation. We used it, I think it was in lecture 2. Alright, now for oscillations of small amplitudes, sine theta can be replaced by theta, and therefore this equation is linearized to equation 13.3. Theta double dot plus 3 times gravitational acceleration divided by 2 times the length times theta equals 0. And this equation 13.13 has the same form as that of 13.8. Okay, if I can just go back. There we go. X double dot is plus k over m x equals 0. It has the same form. Here we have theta double dot and theta, and we've got this term over here. So, therefore, we can say the natural frequency of this oscillating pendulum is the square root of 3g over 2l. Now, assuming that L is 1 and gravitational acceleration is 9.81 meter per second square, L is obviously also in meter. The time period is found to be 3.836 seconds, hence the integration time step should be delta t less than 0.38, which is 1/10 of tau. Alright, so for our pendulum rod, we have a length of 0.6 meter, and therefore equation 13.14 yields for the natural frequency being 4.95 Hertz. So for our pendulum rod, the time period then follows from equation 13.11 as tau equals 2 pi over omega. Let me just show that quickly. There we go, 2 pi over omega. So we can calculate that as 1.27 rounded off seconds. Hence the integration time step should be less than 1/10 of the time period, which gives us an integration time step of less than 0.127 seconds. Alright, now to see how damping affects the natural frequencies, remember, just to recap, so we are busy with integration time step, and the size of the integration time step should be adjusted based on the natural frequency of the system. Okay, and this is now fixed integration time steps. In a little bit we'll talk about adjustable or adjusted time steps, which is obviously much more efficient to use. Okay, but this is just some background, so please bear with me. Okay, let's look at the effects of damping on the natural frequencies and hence the selection of the time steps. So we need to revise equation 13.8 to include damping, where d subscript c is the damping coefficient. Okay, so this gives us equation 13.15. X double dot plus the damping coefficient divided by m x dot plus the spring stiffness divided by mx equals 0. For convenience, we define the damping ratio zeta as the damping coefficient divided by 2 times the square root of the spring stiffness multiplied by the mass. With this definition, equation 13.15 is expressed as x double dot plus 2 zeta omega x dot plus omega squared x equals 0. In this equation, omega, the natural frequency, is square root of the spring stiffness divided by m, is the undamped frequency as defined in equation 1310. The damped frequency is expressed as the undamped frequency multiplied by the square root of 1 minus zeta squared. Now, figure 13.2 shows the solution of equation 13.15 for three different values of damping ratio, where it is assumed that omega is 2 pi radians per second and the initial conditions x equals 1 and x dot equals 0. For the case where zeta, the damping coefficient, is 0,2, the damping ratio, zeta is 0,2, the response begins to decay. If we look at figure 13.2, we can see the dashed line, there's a decay in the response. Now, as long as zeta is greater than 0 and smaller than 1, the system is called underdamped. We note that for this response, the damped frequency is slightly smaller than the undamped frequency, which is given as 2 pi radians per second. Okay, and that follows from equation 13.8. The fact that zeta is between 0 and 1 will ensure that the square root of this term is also smaller than 1. So hence, our damped frequency is smaller than the undamped frequency. Now, when zeta equals 1, the system is critically damped, for which omega, the damped frequency, is then 0. Okay, if zeta is exactly equal to 1, the damped frequency is 0 times the undamped frequency, which is 0. So we have a critically damped system. In general, since the damped frequency is less than the undamped frequency, for the purpose of time step selection, we should use the undamped frequency as our reference. Alright. The mass spring and pendulum examples that we've looked at show how the time period of the oscillation can be calculated. However, for more complex systems, the calculation of natural frequency will not be that simple. For multi-body systems, the linear realization of equations of motion in explicit form can be rather cumbersome. For systems with more than one degree of freedom, there will be more than one natural frequency. For such systems, the highest frequency must be found and the step size much smaller than the period of the highest frequency must be selected. Now, since the equations of motion are generally nonlinear in terms of coordinates, linear realization of these equations yields a time step which is valid only for the configuration around which the system has been linearized. In a different configuration, the linearization process may yield a different time period and consequently a different time step. To avoid the difficulties associated with the selection of a proper size for the time step, it is strongly recommended that a variable step size algorithm be used. Many well-developed algorithms are available that determine a proper time step and will automatically adjust the time step during the course of a simulation. One such algorithm is the ODE 45 algorithm in Matlab. The function ODE 45 can be utilized as follows, as shown on the screen. Okay, the input arguments are these three arguments over here, or the function where the equations of motion are constructed and solved. Okay, this is this at example. The reporting time interval delta t that should be specified in t span as the starting time an array of starting with the starting time, incremented with the time step up to the final time. Okay? If delta t, the time step, is not stated in t span, the ODE45 algorithm will report the results at every integration time step, which is now obviously an adjustable time step. Now, Z, the third input argument, is the integration array containing the initial conditions on the variables. In other words, our coordinates and velocities. Now, the output of this ODE45 algorithm contains two arrays. The column array T contains the time marks of the integration. The time array, the array ZT contains the time record of the transpose of U, which is the coordinates and velocities. The accelerations are not returned from the algorithm ODE45. If the accelerations are needed, they must be recomputed by solving the equations of motion as algebraic equations at every time step. Alright, and that summarizes the variable step size algorithm, and we were talking about size of integration time step, and this formed part of the integration time step size subsection that we discussed. Okay, so let's look at subsection 13.2, constrained formulation. Okay, up to now we have focused our discussion on the unconstrained formulation, which really gave a theoretical overview of what is involved in forward dynamic analysis for what are involved in a forward dynamic analysis. Now, the constrained formulation is obviously now a bit more relevant to what we are discussing and to our pendulum rod example. The constrained equations of motion, including all kinematic constraints, are expressed as. Now, equations 1319 to 1322 could represent a system of constrained particles, a set of bodies formulated in body coordinates, or a closed chain system represented by joint coordinates. Now, system of constrained particles is not something we will consider in this module, as is the closed chain system represented by joint coordinates, but they are listed here for completeness sake as per Planar Multibody Dynamics, the textbook written by Prof. Nikravish. And in the textbook, this joint coordinate formulation is also dealt with in a lot of detail. Alright, so, but what we have considered so far, and what we will obviously look at in more detail, is a set of bodies formulated in body constraints. Okay, so, and this is also now the example that we will discuss in more detail in this lecture, what I call the forward dynamics pendulum rod. Okay, so it's exactly the same pendulum rod as for the inverse dynamics. The only difference is we are not prescribing the angular motion of this pendulum rod. We are applying a torque, and then we want to calculate what the accelerations, what the angular response of the pendulum rod is. Alright, so let's just have a look. I will have to zoom out a little bit. Okay, let's do that. Okay, so for this forward dynamics pendulum rod, equation 13.19 becomes, okay, and this is the positional constraints that we've derived in the previous lecture. Okay, so nothing new there. Equation 1320 is also not new. It's something that we did show in the previous lecture. The velocity constraints for the pendulum rods exactly the same. What is new is 1321. Alright, so the acceleration equations being the Jacobian matrix multiplied by the centroidal accelerations plus the right side, what we call the right hand side of the acceleration equations, and that equals 0. Right. Okay. I think we did mention it in lecture 3, so you can just have a look. But anyway, there it is given in this lecture as well for completeness sake. Alright. Now, what does 1322 then look like? It's the mass or inertia matrix multiplied by the centroidal accelerations. In this case, our external forces and moments acting on the mechanism will look like, let me just zoom in a little bit. Okay, so our external forces acting on the mechanism, external forces and torques, are the weight in the negative y direction. That's why it's minus mass times gravitational acceleration, plus this torque or moment n. Okay, and that equals, if I can zoom out again, okay, so in this case the moment acting on the mechanism is included in this column vector, okay, and that equals then the transpose of the Jacobian matrix multiplied by the Lagrange multipliers associated with the revolute or pin joint. Okay, very simple. Alright, so okay, that is how we will formulate our constrained multi-body system in body coordinates. Now, getting back to the 4 equations that we've listed, these equations can be treated as linear algebraic equations if the coordinates and velocities are known and the accelerations and Lagrange multipliers are unknown. Okay. So when the unknowns are the coordinates and velocities, the same equations must be treated as a second order mixed differential algebraic equations. Okay, and we'll explain what we mean by that in the next few minutes. Okay, so to solve equation 1322 for the accelerations, we append it to the acceleration constraints of equation 1321 to form the following set of equations given by equation 1323. Right. Now for our forward dynamics pendulum rod, equation 1323 becomes, alright, let me just zoom out a little bit. Okay, and it's given here. So it's the compounded matrix consisting of the mass or inertia matrix, right? Then the transpose of the Jacobian over here is the Jacobian matrix, and then a 2 by 2 zero matrix completes this matrix on the left. Okay, we have the centroidal accelerations, so x1 double dot, y1 double dot, phi1 double dot, and the Lagrange multipliers, lambda 1 and lambda 2. And then we have the external forces and moments acting on the mechanism, which in our case is just weight. There's no external forces acting in the x direction. In the negative y direction, there's mass times gravitational acceleration. and then there's the moment n acting on the body, okay, and then this is the right hand side of the acceleration equations, gamma, okay, consists of those two terms for the single pin or revolute joint that we have. Alright, so let's now look at the next line of thought. Knowing the coordinates and velocities, the equations represented by 1323 can be solved for q double dot and lambda. Alright, so let's just look at what we have. So if that statement makes sense, okay, what they say is knowing the coordinates and velocities. Okay, so obviously the mass will be known as will the moment of inertia. The local coordinates CA1 and eta A1, those are known. Then we need the coordinate. We need the coordinate phi, the angle phi, which is one of the coordinates. We need to know that. Then this matrix is known. Okay. Then on the right hand side, okay, we know the mass, gravitational acceleration is known. The moment acting on the pendulum rod is also known. It's something that we specify. And then coordinate phi 1 must be known, plus the angular velocity phi 1 double dot must also be known. Then the right hand side is known. Okay, and that's what they say. Then with the coordinates and velocities known, we can solve equation 1323 for the accelerations and the Lagrange multipliers. Now, considering equation 1322 as a differential, okay, let me just zoom in a little bit again. Considering equation 1322 as differential equations, two integration arrays are defined similar to the unconstrained formulation. Okay, so this is something we did speak about earlier. And just for completeness sake, very trivial, for our forward dynamics pendulum rod, equation 1324 becomes x1, y1, phi 1, x1 dot, y1 dot, phi 1 dot, and u dot becomes x1 dot, y1 dot, phi 1 dot, x1 double dot, y1 double dot, phi 1 double dot. Okay, very trivial. All right. Now we integrate u dot, which contains velocities and accelerations. We obtain, let me just repeat that. If we integrate u dot, which contains velocities and accelerations, we obtain u that contains the coordinates and velocities for the next time step. Okay? This requires a set of initial values for coordinates and velocities to start the integration. The initial values of the coordinates and velocities must satisfy the position and velocity constraints respectively. Okay, that makes sense. Now the coefficient matrix in equation 1323 contains numerous zero entries. Alright, let me just expand this once again. Okay, we'll get to that in a minute. The mass or inertia matrix is a diagonal matrix in body coordinate formulation. D, the Jacobian, contains many zeros, and we also have the zero n number of constraints by number of constraints matrix at the lower right corner. Okay, let me just show that here. It's very visible, very easy to see. Okay, so there's the diagonal matrix. Our Jacobian matrix transpose contains zeros. Here there are zeros, and obviously the 2 by 2 zero matrix here at the bottom right corner. Alright. Now, any operation on such a matrix, okay, let me just zoom out again. Alright, so any operation on such a matrix in the process of determining the accelerations and Lagrange multipliers may computationally be inefficient. Okay, now to improve the computational efficiency, we can obtain the solution in a two-step process. Okay, and we are now still considering this equation 1323. Alright, so we want to improve the computational efficiency using a two-step process. Now for that purpose, we rewrite equation 1322 as, okay, and let me just go back to 1322 just to show you. Okay, 1322 is the equations of motion for this constrained system. Okay, so we rewrite it, we shuffle the terms, we isolate basically the centroidal accelerations on the left-hand side of the equation. So we need to move this mass or inertia matrix to the right-hand side. Okay, so let's see what that looks like. Okay, 1325. Let's see what it looks like for our forward dynamics pendulum rod. Okay, now we have the centroidal accelerations of the pendulum rod on the left-hand side. On the right-hand side, we've got the inverse of the mass matrix. Okay, now that is simply 1 over m1, 1 over m1, 1 over j1. And how do I know that? Because the definition of the inverse of a matrix, if you take the original matrix and multiply it with the inverse of the matrix, you will get the identity matrix. Okay, so the original matrix had in the diagonal, on the diagonal, m1, m1, j1. Okay, so m1 multiplied by 1 over m1 equals 1. Same for this term and the same for that term. So that's how I got the inverse of the mass matrix. Okay, then in brackets, let me just zoom out a little bit. In brackets, we have the external forces and moments acting on the pendulum rod. And we have the transpose plus the transpose of the Jacobian multiplied by the Lagrange multipliers. Very simple. Okay, I've populated this equation further with the values we have. Okay, so what we get then, the centroidal accelerations of the pendulum rod equals 1 over 2, 1 over 2, 1 over 1, 0,06. The external forces and moments acting on this system is 0, 2 kilograms times 9,81 gravitational acceleration, and the moment I selected as 6, and you will see why in a little bit. Okay, so just bear with me. It's 6 Newton meters, counterclockwise. Right, this is then the substituting the values for CA1 and eta A1. Eta A1 is obviously 0, as I've shown many times in the previous lectures. Just to have a look. Okay, so that those terms fall away. We only have a CA1 component, which is minus 0,3. Okay, the initial angle phi 1, this is now at time t0 obviously. The initial angle phi 1 is minus pi over 6 radians, which equals minus 30 degrees. Lambda 1 and lambda 2. Okay, so, right, let's carry on. Then we substitute the preceding 1325 into 1321 and rearrange the terms. Okay, let me just quickly show you what 1321 looks like. Okay, 1321 is the acceleration constraint equations, right? Okay. So what we did is we isolated q double dot and then we substituted it here into 1321 and rearranged the terms. and then we get this equation 1326. Alright, so let's see what that looks like for our forward dynamics pendulum rod. Okay, I will have to zoom out again. Okay, no, not necessary. Right, that's good enough. Alright, so we've got the Jacobian matrix D, the inverse of the mass matrix, mass or inertia matrix, the transpose of the Jacobian matrix. Okay, so the Jacobian matrix is a 2 by 3. Okay, 2 rows, 3 columns. The transpose of the Jacobian matrix is then a 3 by 2, 3 rows and 2 columns. The 2 Lagrange multipliers, and that is equal to gamma, which is the right hand side of the acceleration equations. And in our case, for this single pin joint or revolute joint, it's a 2 by 1 column vector, okay, which looks like this, okay, minus the, once again, the Jacobian matrix, a 2 by 3, the inverse of the mass matrix multiplied by the external forces and moments acting on the mechanism. Alright, so let's see what if we can simplify it a little bit. Okay, so I've substituted once again for the Jacobian matrix the values of Chi A1 and Eta A1, as well as the initial orientation minus pi over 6. This is only at time t0, okay, so we're looking at that time instant, which is obviously where we start our analysis and integration, okay. That's straightforward. I did speak about the inverse, yes, the inverse of the mass or inertia matrix. Okay, this is the transpose of the Jacobian, Lagrange multipliers, Jacobian, inverse of the mass matrix, and once again we can substitute the values. The mass is 2 kilograms, 9,81 gravitational acceleration, and bear with me, you will see why I selected 6 Newton meters as the torque acting on this driven pendulum. Okay, so now this, and we're heading somewhere, just bear with me. Right, so if we multiply out these two matrices, the first two matrices, we get, this is a 2 by 3, this is a 3 by 3, so we end up with a 2 by 3, which is shown here, and you can check the maths on your own time. Alright, and we can do the same over here. Okay, so once again, the Jacobian matrix, the 2 by 3 multiplied by the 3 by 3 inverse of the mass or inertia matrix, that gives a 2 by 3. Alright, and that this is obviously a 3 by 1 column vector. Okay, now we end up with what we have over here. I've summarized it here. So this is a 2 by 3, 2 rows, 3 columns matrix. This is a 3 by 2, okay, 3 rows and 2 columns, multiplied by lambda 1 and lambda 2. On the right hand side we have once again a 2 by 3, 2 rows, 3 columns, and we've got this column vector over here. Now what that simplifies to is a 2 by 2 multiplied by the 2 Lagrange multipliers, and that equals a 2 by 3 multiplied by that column vector. Okay, so the fact, what I've shown here now in a very elaborate explanation, is that for our pendulum rod, this Jacobian multiplied by the inverse of the mass or inertia matrix multiplied by the transpose of the Jacobian, that yields a square matrix. Okay, that's the whole point of all that explanation. Okay, and this is the point that Prof. Nikravesh is making over here. Since the product, okay, Jacobian, inverse of the mass or inertia matrix, transpose of the Jacobian is a square matrix, we first solve equation 1326 for lambda, okay, and then we solve equation 1325 for the accelerations. Okay, yeah, that makes sense. Okay, so if I can just show you here, yes, so as you can see here, right, maybe let me go to this. It doesn't matter. Okay, I can work with this. All right. So this follows from the mass. That term follows from the moment of inertia. Now this term needs the orientation at the current time step, which we know. We know the initial conditions of our mechanism. Okay, so that's known. Once again, that also follows from the orientation of the current at the current time step. Okay, we don't know the Lagrange multipliers at the current time step. We don't know that. But once again, on the right hand side, we know the orientation at the current time step, and we know the external forces. Okay, that's weight, that's straightforward, and we know the moment that we are applying. So we can solve this equation to find the Lagrange multipliers at the current time step. Okay, and with that, if we have the Lagrange multipliers at the current time step, okay, we go to equation 1325. Now, let me show you in this form over here. Okay, so we don't know, we want to calculate the accelerations at the current time step, at the initial or current time step. That's known, mass and moment of inertia, the external forces and moments acting on the pendulum rod is known, the current orientation is known. Okay, so that's where this minus pi over 6 comes from, and we've just calculated the Lagrange multipliers. So now we can find the accelerations at the current time step. Okay, and if we have that, what we can then do, okay, we can then, so now at the current time step we have the velocities, okay, because we know the initial velocities also at time t0. We've calculated the initial accelerations, all right, at the current time step. We also have the initial positions and velocities. So now we can integrate to find the the positions, the positions and orientation at the next time step, as well as the velocities at the next time step. Okay, and that's what we discussed earlier in this lecture in a lengthy explanation. All right, so then, and this is how we solve the dynamics for our pendulum rod or any constrained multi-body mechanism for that matter. So just to wrap up what I just said, I'm going to repeat that. Nikravesh explains it also very systematically. So we now looked at the constraint equations of motion, including all kinematic constraints. All right. Now let's look at the initial conditions. Now, solving the second order differential equations requires initial conditions on the coordinates and velocities. Alright, that is something we said a minute ago. Alright, although these initial conditions must represent the state of the system at the initial time, in general, for unconstrained equations, the initial conditions may be assigned arbitrary values. Alright, that's for unconstrained equations. Alright, that's just a side note. Don't get confused. Okay, but when the system is constrained, in other words, when there are kinematic joints, the initial conditions must satisfy the constraints at the position and velocity levels. Okay, and now, okay, just for the moment, consider the top equations of 1327 and 1328. Alright, this we've looked at many times. These are the kinematic position constraints associated with the joints. Alright, and that's the time derivative of the position constraints, the velocity constraint equations associated with the joints that hold the mechanism together. Okay. The bottom ones we discussed in the previous lecture. Alright, these are the driver kinematic constraints and the driver velocity constraint equations. We've discussed that in the previous lecture. Alright, so let's see. In these equations, we've considered the possibility of the driver type constraints that might be present. Okay, and in an example that I will show a little bit later, you will see how we can include both in Integra's Matlab algorithm. Alright. If we start numerical integration with a set of initial conditions that do not satisfy the constraints, most likely the integrated response will be erroneous. Now, chapter 14 discusses several methods to assure the initial conditions do not violate the constraints. And you are welcome to have a look at chapter 14 if you are interested in that. Alright, so that's initial conditions. Now, let's look at the general integration procedure. Alright, so assume a multi-body system with n degrees of freedom as represented by a set of n subscript v coordinates and nv minus n degrees of freedom independent kinematic constraints. A process for forward dynamic analysis can be stated as in the following algorithm. Okay, and this is given by algorithm C. So we define the initial conditions for the coordinates and velocities, Q0 and Q dot naught. The initial conditions must satisfy the constraints at the coordinate and velocity levels. Then we initialize the integration array as U equals Q0, Q dot naught. We establish the time parameters for integration, and we utilize a numerical integrator such as ODE 45, which is a variable step size integrator, as we discussed earlier in this lecture. We send this initialized integration array and other necessary data to the integrator. Now, the numerical integrators such as ODE 45 will send this initialized vector u for t equals it, the current time step, to function c and asks for u dot, right, which contains the velocities and accelerations at the current time step. Alright? This function constructs and solves the equations of motion for accelerations and Lagrange multipliers and returns u dot to the integrator. The integrator returns the computed coordinates and velocities for every time step. Okay. And you're welcome to have a look then also at example 13.5. Okay, so that concludes our discussion, our theoretical discussion of the forward dynamic analysis of the pendulum rod. Next, we will look at how do we actually perform the analysis using Prof. Nikravesh's Matlab code. Okay, so let's look at the input files that I used to simulate the forward dynamics of the pendulum rod. Okay, I've opened the files. They are listed in alphabetic order as they are in the model subdirectory. Alright, so inanimate is exactly the same as before, with the limits being minus 0.75 and plus 0.75 meters respectively, both in the x and y directions. In bodies is also exactly the same. Just note that as before, if you don't specify the initial velocities of body 1, the default value is used, which in our case is correct. The default value of 0, 0 is indeed correct. Okay, so in forces, here there is a difference. Force S1 is weight, okay, as before, but force S2 is now of type T, which is a torque. The body index, I body index, is body 1, okay, and if you remember, body 1 is our pendulum rod, and S2.T equals 6, that's the magnitude of the torque, 6 Newton meters, which I've mentioned earlier. Why did I choose 6 Newton meter? Okay, if I can quickly just show you this graph. This is the graph of the inverse dynamic analysis that we performed in lecture 3, and the input torque required to accelerate the pendulum rod in a counterclockwise direction at 2 pi over 60 radians per second squared what is shown on this graph, and it varies between just less than 6 Newton meters and just more than minus 6 Newton meters. Okay, so 6 Newton meters is just above the amplitude, the maximum magnitude of the input torque that we calculated for the inverse dynamic analysis. Okay, so that's why just on a broad sense why we selected that. Okay, and I'll show you in a minute what happens if you select an input torque that is less than 6 Newton meters. All right, or less than this maximum here. Okay, so our forces, we list both of them, S1 and S2, in this list over here at the bottom. Okay, infuncts are empty. The function infuncts is empty, I should say. In joints, we now revert back to the single revolute joint that we defined earlier. Okay, it's different from the inverse dynamic analysis. In points is exactly the same as before, points 1, 2, and 3. Point 1 being on ground, point 2 being on body 1, and point 3 also being on body 1. And in U vectors is also empty. Alright, so we then, I can clear all of this, sorry. Let us run the simulation. So we enter DAP. It is pendulum rod D, a folder that contains the model. Yes, we do want to correct the initial conditions. This is as before, x, y, and phi in degrees, corrected velocities. What is the final time? We will select 3 seconds. The reporting time step, let's make it 0,01. Okay, and there it goes. Okay, what we are interested in is the animation. Alright, and there it's barely enough to start rotating. Okay, but once it starts, it does not stop, obviously, because we are applying a constant torque of 6 Newton meters. And now you can see how quickly it gains rotational velocity. Okay, so you will now obviously, in order to get the parameters and the variables that we are interested in, you will type in the word post, and that will yield all the variables. What I've done already is I've copied all the variables and populated my spreadsheet. That's what you see over here. Now, I'm not going to compare the calculated reaction force with the analytical calculation. You are welcome to do that on your own if you prefer. I certainly do trust the values that are calculated here. Let me show you the results. So this is the trace of the center of gravity of the pendulum rod, and the trend is the same as before. The aspect ratio is wrong, but the intersection is at plus 0,3 in the y, minus 0,3 in the x, minus 0,3 on the y, and plus 0,3 on the x. What you see here is a little bit worrying. There's a double line which can't be right. Okay, and what it is the reporting time step that we've stipulated is 2 cores for the speed at which this pendulum rod is rotating. All right. Now, to confirm that, to support that statement, have a look at the coordinates of the pendulum rod. All right. So you can see that initially it's a smooth curve. Okay, but as time goes by, it seems to miss some of the peaks. Okay, that peak must obviously be at 0,3, and that's because the reporting time step for our that we selected is 2 cores. Okay, if we were to select a finer reporting time in step, it would have captured that data. All right. Be that as it may, you can see that phi varies quadratically, starting at minus 30 degrees. It's not very clear here. It's on the secondary y-axis, and it goes all the way to 3000 degrees, even in a short time span of 3 seconds. Okay, the velocities, similar behavior, starting from 0, okay, and accelerating or varying periodically with a shorter and shorter period, going up all the way to 15 meters per second, okay, for the x and the y, okay, and this shows the angular velocity of the orientation angle. So it's not a smooth curve. It also varies periodically as time goes by, and it goes all the way up to 50 radians per second. All right, so our accelerations, X and Y accelerations are plotted against the primary Y axis. It goes up all the way to almost 800 meters per second squared. The rotational acceleration varies also periodically, but the amplitude of the angular acceleration does not change. Alright, it remains the same, although the period does shorten. Okay, let's have a look at the Lagrange multipliers. Lambda 1 and 2, they are plotted against the primary y-axis, and they go up all the way to 1500. Now remember, these Lagrange multipliers represent the reaction forces. So I've isolated the reaction forces now on the next graph, and here you can see the resultant reaction force, how it peaks at more than 1.5 kilonewton for a simple pendulum rod weighing 2 kilograms and a torque of 6 Newton meters being applied to it. Okay, so it's quite an interesting result. Doing a sanity check on these results, one will have to dive into the maths a bit deeper, but I do trust them based on my previous simulations that I ran and that I've shown you. Okay, so it's a very interesting and counterintuitive result, thinking that a pendulum rod of 2 kilograms having a torque of 6 Newton meters applied to it within 3 seconds, the resultant reaction force peaks 1.5 kilonewton. It's counterintuitive, but we do trust the maths, and therefore we do trust our simulation. And we also did sanity checks on simpler simulations before we presented these results. So all is good. Alright, so let me show you quickly what happens if we change the force to 5 Newton meters. Okay, so let me just save that quickly. Go to the command window, I clear okay, yes, I want to correct the initial conditions. Once again, 3 seconds, 0.01. Okay, and now we look at the animation. And now you can see the torque is not enough to rotate the pendulum rod counterclockwise. It sort of, it pivots there, it sits there. It goes down slightly and picks up slightly. It's barely visible in this animation. Right, let me, it's still going. Alright, let me change the input torque to something smaller. Let's use 3 Newton meters. Okay, once again 3 seconds, 0.01. Okay, and we say anim. Okay, now the torque is a lot, well, it is too small, so the pendulum starts falling and then the torque picks it up. The pendulum will fall again and it will pick up again. So and it will continue with these oscillations. Alright, Okay, so my next example, I just want to quickly change this back to 6 Newton meters. Alright, so my next example that I want to show you is again the pendulum rod. But in this case, let me just open the input files quickly. Okay, so inanimate stays the same as before, in body is also the same. In forces now, yes, it also stays the same as before. So we've got weight as S1 and we've got this torque of 6 Newton meters as S2. Right. Now we have, let me jump to in joints first. So I've got the revolute joint that we specified earlier, and we also now have the relative rotation joint. So I'm combining the forward dynamics and the inverse dynamics. I'm combining the two. All right. So I've got this relative rotation joint that I've specified for the inverse dynamic analysis, and it refers to function number 1, which is exactly the same function that we had for the inverse dynamic analysis. In points is the same as before, point 1, 2, and 3, and in U vectors is an empty vector. Okay, so let's run the simulation and see what happens. Okay, we go to the command window, we clear the variables, we clear the command window itself, and we enter DAP. Our folder is pendulum rod E. Do you want to correct? Yes. I'm going to go for a 30-second final time, 0.06. Okay, let's see what happens. Okay, and now we're applying a torque of 6 Newton meters, but we're specifying that the angular acceleration can only be 2 pi over 60 radians per second squared. So hence, we must, and the simulation is calculating what I call a braking torque. It's braking the torque that we are applying in order to yield the prescribed angular rotation. And that's actually amazing that this algorithm is capable of doing that. I think it's amazing. Alright, so let me show you. If you don't believe me, I'll show you in a minute. So the results are in fact, well, in terms of positions, velocities and accelerations, the results are exactly the same as for our inverse dynamic analysis that we performed in lecture 3. Okay, and let me show you. I've copied. You can obviously, you need to run post. Okay, and what I've done is I've copied all the variables into my spreadsheet. I shouldn't have. Okay, let me just zoom out a little bit. Okay, so the trace of the pendulum, nothing new. It's exactly as it is supposed to be. Coordinates, and there you can see it varies. The x and y coordinates varies between plus 0,3 and minus 0,3, and the orientation angle varies from minus 30 degrees all the way to 2,500 degrees. Velocities are exactly as before. Here you can see the angular velocity. A straight line starts at 0, goes to just above 3 radians per second squared. You will recognize this graph from our inverse dynamic analysis graph. Accelerations, there you can see them. X, Y, and the phi acceleration just over 0,1 radians per second square, which equals 2 pi over 60 radians per second square. Lagrange multipliers. Right, let's have a look. This is now different. Lagrange multiplier 1 and 2 will be the same as before. Okay, you can compare it offline if you like, but Lagrange multiplier 3 varies now on the secondary y-axis between approximately minus 12 Newton meters to 0 Newton meters. Okay, so what I've done is and I'll show you in a minute. Okay, the reaction forces are exactly the same as before. It can't be different because the resultant motion of the pendulum rod is exactly as before. But the torques applied on the pendulum rod is different. Okay, we have a constant torque of 6 Newton meters. Okay, and it's counterclockwise, hence it's positive. Then we have the inverse dynamic analysis torque that we calculated. Okay, this is now related to lambda 3. Okay, it varies between just more than minus 12 Newton meters to just less than 0. And when we add those two together at each time instant, we get the resultant torque that is applied on this pendulum rod. And this is this purple line. And there you will notice it varies once again between just less than 6 and just more than minus 6 Newton meters. Right, which is what we had for lambda 3 in the inverse dynamic analysis. Okay, so once again, I think it's an amazing result. The fact that we can do both, we can specify a motion, we can specify an external force, and the algorithm incorporates both the inverse dynamic analysis into the forward dynamic analysis, if you like. Okay, and this is now my layman term. In actual fact, a better way of saying it is this algorithm performs a dynamic analysis, be it inverse, be it forward, or a combination of the two. Amazing that this piece of software is available for us. So I think one can only say thank you very much to Professor Nikravesh for his amazing work. It's really a culmination of a lifetime of work that he's put into this textbook, and I think it's amazing. And the Matlab tool is available, and one can obviously expand on it, yes, but the solid foundation is there, and I really think it's something that one can salute Professor Nikravesh for. And with that, thank you very much for watching.